Hello and welcome to a short tutorial on chair conformations and how to go from a 2D structure to a 3D structure. All right, so before what we talked about is that in cyclohexane chair conformations, what you have is some structure like this, and it has hydrogens either in axial positions that are perpendicular to the two carbons that make up the seat of the chair, or it has equatorial substituents that are perpendicular to the two carbons that make up the seat of the chair. And remember, the seat of the chair that we're talking about is this bond. So the four carbons there that meet together to make up that seat, if you could imagine sitting down in that chair. All right, so the reason why we're having this multi-tutorial is because sometimes you need to look at a structure like this, and you need to be able to turn that into a chair conformation. Or you need to be able to look at a chair conformation, and you need to be able to turn that structure into a 2D bond wedge, or sorry, a wedge dash cyclohexane structure. So let's have a look and see how we can do that and how we can systematically be able to do this each time without fail. All right, so let's look at the first example first. So in this example, we have our cyclohexane ring, right? And we see that in the one carbon position, we'll just label them 1, 2, 3, 4, 5, 6. That should be a 1, not a scribbly. The chlorine is pointed up. So let's just choose a carbon to start with. Let's make it be 1, 2, 3, 4, 5, 6. Because I went, if you can tell, I went clockwise around here. And here I'm also going clockwise. All right. So the chlorine, which I will color, I'll color it in purple, is here. And we'll say that the bromine, I'll color in maybe green here. Great. So the chlorine is pointed up in number 1. So that would be pointed up. That would be pointed up. And of course, the opposite case is where the hydrogen is pointed back, right? So the hydrogen here would be pointed this way. Okay, in carbon number 2, we have the bromine going back, which means the hydrogen is going up. So the bromine needs to be going back. In other words, in an axial position, and the hydrogen has to be pointed up. So if you notice that they have two different signs, the chlorine is on a wedge and the bromine is on a dash, which means that they are here both axial in this case. But I know what you're thinking, and you're thinking, how did I know to draw them both in the axial position if they're going up? And that comes from looking at the 3D representation of this molecule. So what I'm going to do is I'm going to stop the share here so that we can have a look at a model kit. Because like I said before, the model kits can be very useful here we are. Okay. So what we have here is a 2D representation of cyclohexane, right? It's totally flat. There's no conformation here. All we see is that there are 2 substituents on each of these carbons, right? Okay, so what I've done is that I've put red and blue on each one of these carbons because in the drawing that we just made, we said that the 1,2 position, like we just saw, in this example, leads us to both of these being axial, one pointed up and one pointed down. So that's why the colors on the cyclohexane are as they are. All right. So now what if we turn this into a chair? What happens then? Okay. So I'm going to bend one up and bend one back. There we go. Okay. So now we have a chair, just like we were drawing before. And if you notice that we have, again, the 4 carbons that make up the seat of the chair, the footrest, and the headrest of the chair. Okay, so let's imagine now. Okay, so let's imagine now that we are, instead of just looking at some random chair, we are now looking at the 2D representation of the chair that I just drew. So once again, I'm going to put our little model into its 2D form here. And so now I've traded out a couple of those blue substituents for one yellow and one white and teal, which we'll just call white from here on, substituents. So the yellow one we're going to say is the chlorine, and that kind of greenish one we're going to say is bromine. So in our 2D representation, remember, the chlorine was coming towards us, which it's now doing, and the bromine, the green and white one, was going away from us, which it's also doing, right? Okay, so now I'm going to bend this into a chair, and then we'll see how how we could know that both of these would be axial. All right. So we start by making a headrest on one side, and then making a footrest on the other. There we go. We have our nice comfy looking chair. Voila, there we have it. So you can see here that in this case, the yellow, what we were calling the chlorine, was coming out at us originally, and it is now pointed straight up, right? And the bromine, whereas it was in a dash going away from us, is now pointed straight down, but both are in axial positions. So that means that each axial position must be pointed up or down in an alternating fashion around the ring. And you can see a little better about how this happens by looking at this axial one, right? And this one, and watching what happens whenever we straighten it out. Okay, we just straightened it. So now you can see that both are pointed in opposite directions, right? One towards you and one away from you. And that alternates around the ring. So if we were to go back to our notebook, and we were again to have a look at this cyclohexane, we could say that every axial position, we'll just call it A here, every axial position will be alternating wedges and dashes in the 2D structure. Whereas the E's alternate the opposite way. If we were to draw the E's, let's do this in blue. The E's, again, are going parallel, equatorial positions. The E's will be alternating the other way. So that means if you were to have, just like this, a 1,2 di-substituted cyclohexane with one on a wedge and one on a dash, both of those substituents have to either both be axial or equatorial. And this has been the tutorial on cyclohexane chair conformation switching.